Hello, ready to go on with the last problem of section 6. So we have to evaluate an integral, and the only idea I have is to make a trigonometric substitution for t. So t goes from 0 to 1 like this, and that's t, and we would like u to go from -1 to 1. So defining t as so it's much easier to go from t to u. So I'll do that. So the slope is 2 and 0 goes to -1. So t equals u plus 1 divided by 2. That's correct. And then set u equals 2, and it goes from -1 to 1, so that's sine I would like, where x goes from minus pi halves to pi halves. So let's do this one at a time, or well. We'll do it as 1. T equals sine x plus 1 divided by 2 dt cosine x dx. And square root t times t minus 1. Well, let's do it step by step. So it's u plus 1 halves, and then u minus 1 halves being multiplied. And u was sine x. Now that's weird, because it was positive all the way here. The part of under the square root is positive here, isn't it? Yes, indeed. And it's positive here. That's the point. It's 1 minus t. We have to correct it because that's it's just changing the sign, so it shouldn't be so difficult after all. T times 1 minus t u times 1 minus u 1 1 minus u squared, 1 minus sine squared, and that's cosine x halves. Alrighty, so let's make the substitution. T to the nth and the denominator, the denominator we have here, that's 2 divided by cosine x, and dt is 1/2 cosine x dx. So they cancel. All right. Now, if n is nothing, maybe it's pi halves, who knows? Oh, that's simple. Now we call this in. I had a feeling all the time we would be using induction. So in. So I get 2 pi. Does that agree with the result? N is 0, so it's pi. They say it's minus a half pi, minus 1/2 pi. It does make sense that you'd give them half pi. So, oh, it's pi halves here. So we're down to pi. So we're just a factor 2 off. Wonder what I did there. There we go. So Very annoying. I can't find this factor 2. Sorry about that. Still got a little sore throat. Oh, not sore, it's just irritated. So let's just checkmate. It's really simple. I mean, it's practically high school. So. Hello. Did you see that? It gives pi, which was somewhat like what I got. So why doesn't this say pi? Oh, this formula only holds for n equals 1 positive, because this product is empty when n is 0. Oh my god. All right. There are some tricks when dealing with powers of sine. I wonder if we could use a trigonometric transformation here. No. Don't think it helps. So the brute force method is to expand the binomial form here, the binomial power. Let's see if that gives anything. That was it, wasn't it? Sinus x plus 1. And they all will contribute. So we are going from minus pi halves to pi halves. That's cosine, so that gives 2 sinus squared. That gives the same as cosine squared, so that's half the length of this guy. Where's the power pi? So this ought to vanish. Oh, it does. Of course it does, because sine is an odd function. So it's only even powers contribute. And this is an average 1/2. So it gives half the length of the interval. I've seen formulas for this, so I feel a little annoyed that I should be doing this. I'd really very much like a cup of coffee and then look it up in Handbook of Mathematical Functions. That would really be easy. So what can we do if we're stranded on what it's called, a desolate island? Partial integration. Differentiating this, taking an integral of this. When the integral of this is cosine, and plugging in the limits give naught. So it's minus the integral of this guy differentiated. And the integral to sine is minus cosine. So that eats that, and then cosine squared, which equals so first it's unity minus sine squared. That was the reduction. And then minus sine squared. All right, so we add this to both sides. That gives 2n. Times, oh, and sine here has, no, that's the integral. Sine 2n minus 2. So that means that no, that's not the integral we're looking for. That's just the power of maybe we could have done it with this guy. Directly. That might have been quite a bit more simple. So let's try that on a new page. So we have the integral over sine x plus 1, and if n is odd, well, I feel more like trotting along with what I'm doing. Now this integral we can call kn. So this integral we can call kn. So kn equals n minus 1 divided by n. Oh, it's k2n. We use the even numbers as index. Kn minus 1, n minus 2. So, and we have the k2 equals pi half. And actually we have k naught as well. Equals pi. So minus so set n to 2, then it's half. That's what it gives, so that's correct. So to find the general formula, we just do a few examples, and then we use induction. K3, that's 2/3 of pi half. And K4, that's pi third. We'll just write it here. Now K4, that's 3/4 of, oh, it's K4. And this is K6. So n is 4, so it's 3/4. And K6, that's 5/6. So it's 2 in halves, and then it's 2, 3, So it's 3 times 5 divided by 2 times 3. So that means it's let's just write it as 2n. And then n was 3 here, so it's 2n minus 1 divided by n faculty. The faculty of n. If n is naught, n. It's just pi, and then when we multiply by 2n minus 1 and divide by n, by 2n we get, so this is obviously correct. Nice. So now we have this sum of these guys. What did we need that for? That was the integrals of those guys. So we need the integrals of that. So it's the integrals of these we need. And it's only the even ones. And then the integral n and then the integral of sine I, which is given by this formula down here. Oh, so when it's only the even ones, then I think we should I is equals to n halves into the division. It's n over 2i, and then n is 2i. Now that was nonsense. N over 2i, and then sine to 2i, so that's the guy down here with I instead of n, pi divided by 2 to the nth, 2 to the ith to I minus 1 divided by 2I, no, I, the faculty of I. This really looks like a dead end. When ending up with this, the only hope is that you can find the expression, and then because of this, the faculty of n divided by the faculty of n minus 2i. 2i faculty may be able to do something, but the rest seems terrible. So maybe we should use the other idea and making partial integration directly on this guy. So that took a long time and believably an errant way. So I'll take a break now, and then I'll try after the break, maybe a cup of coffee, to do partial integration on sine plus 1 to the nth. Or, well, we'll see. I'll just have to think about it a little, because then the odd numbers will give a contribution as well. So, at this moment, I don't know what is sensible to try. So, I've had my break now. So, in order to compute this integral, or this was very fun, but this turned out to be impractical. So, let's try to do it the direct way. So, we just start with this integral and see what we can do. And we write it the same idea as before. Oh, don't like this. Well, but then we split it simply. We split it. So that's I n minus 1 plus the integral and now we do partial integration. The cosine vanishes at the, or minus cosine vanishes at the boundaries, so it's minus the integral. We differentiate this guy, times cosine, and integrate this, which is minus cosine, this is 1 minus sine squared, and that was where I stopped the other time, because we have to write it as 1 plus sine squared. So that was where I stopped the last time. And that was why I didn't choose that road. And we have 1, and what we have is 1 minus sine squared, which can be written, of course, as 1 minus sine, or 1 plus sine times 1 minus sine, and then this is 1 plus sine, so we just forget this. Times 1 and then we have this, we need to have this twice. So that's the point here, that we can actually write this cosine squared as 1 plus sine squared minus 1 plus sine squared plus 2 1 plus sine. So we take this guy first. We just do it blue as this down here, plus 2, and then 1 plus sine, n minus first, and then minus n minus 1 times the integral of 1 plus sine to nth. Go black again. This equals 2n minus 2 plus 1 minus minus n minus 1 in. Oh my god. So n equals 2n minus 1 in minus 1. Wow. So that is an interesting comment on the greedy what is it called, greedy algorithm, doing what seems more simple at first turns out to be very, very difficult, and what seemed slightly more difficult from the beginning, doing this integral, turned out to be very simple. All right, hello. Now we have that was not in, that was I naught. It's very big here. So we have I naught equals pi I1, which was pi halves, and then that doesn't follow this formula, don't really know why, don't care. Of course we can't do the partial integration there. So here, from here on it should work. I2, that's 3 halves. I3 equals times 5 third. Now it's so simple you don't even have to do any induction. All right. So that was A. So we come to the second one. We know that we can get omega 2 from an integral from E1 to infinity. No, omega 2, yeah. And now they define lambda. So we should actually go from from E3 to E2. Instead, and then we hope this will turn out to be this. So we'll just do it again. We have E1, E2, E3, and no, E3, E2, and half omega 2 is the integral from e2 to infinity dt, and that's the same as the integral from e1 to e3. Which was established in exercise, I don't know, it's 12 or 13. All right. So, and now we also get our lambda, e3 minus e1. That doesn't make sense. Oh, that's just a parameter. So we shall change variables, so we integrate from naught to unity. So we must have a new variable. Now we call it t here. So let's call it x equals e3 minus t, divided by e3 minus e1. My God. We integrate from e1 to e3, and it's 4 times t minus e1, t minus e2, t minus e3, dt. And to make the substitution, we need to isolate t. Now what was that? Oh, it's already isolated. So there's no point of doing that. This doesn't make sense. Unity does it. All right. So when x goes from 1 to unity, from naught to unity, then we go from e3 to, it should be e2. This is e1. We go from e1 to e3. So when x is naught, it's e3. When x is unity, it's e1. That was the wrong way. it's t minus e1. Good idea that I check my stuff. So here it works. Why doesn't it here? Layer 1. It doesn't. This works. Well, I had this problem before. I managed to do it with another pen and then downsizing it. It's not quite as clear. I hope you can see it. So it was t minus e1 divided by e3 minus e1. So when t is e1, we get naught. When t is e3, we get unity. And now we isolate for t. There we go. So dt equals oh, that was as if the guy up here was x. So that was just a question of pure confusion. So t goes from e1 to e3, then x goes from naught to unity. Right, so we should change it to an integral over x. So we need to look at the square root, or the thing under the square root. We just take this. Oh, this should, this comes every time. Never mind, let's do it very simple. Let's take it very easy. So times x plus e1 minus e2 times plus e1 minus e3. So we take this out. begins to look like something. This is 1 divided by lambda. And of course, with the numerator being minus the denominator here, it's a minus lambda. And this is x minus 1. So it begins to look like what we should show. And then we multiply this guy with lambda and divide it out here, taking 1, the exponent diminishing it 1 here. All right. So now we can make the substitution from naught to unity, and out of this comes four. That makes a power of 2 out here, which is eaten by nothing, so we just have to write it. And dt so we'll just write the power of 2 first, comes out. Next, dt is e3 minus 1 dx, e3 minus e1, and this is exactly what comes in the denominator from when after taking the square root, so they cancel. So it's 1 divided by, so it's the square root of e2 minus e1, and this is in the denominator, so this comes in the numerator. And then 1 divided by the square root, and then dx. So, was that what we should prove? It's close at least, but let's have a look. 1 divided by square root e2 minus e1, and I have it in the numerator. There's no factor 2, that's lost in translation. And then t, 1 minus t, 1 minus lambda t, or just change signs there. That makes sense because we want both of them to be positive. Of course, that was silly. So there's only this square root that is still being a problem. It should be the square root, but not in the numerator and in the denominator. So where did that come from? That was lambda. So we multiply by lambda, thus we divide by lambda. Thus this one is diminished, and this one should be in the numerator. And therefore this one should be down here. All right, we are almost there. Just a factor 2. If we were only a physicist, then we could say that that comes from quantum mechanics. Oh, it's half omega 2. I computed, so omega 2 cancelled. So, hooray, I've done problem 14b. So, I think that was enough for today. So tomorrow I'll be strong again and can start C. So thank you for now. So it's 20 minutes to 5, and I thought I just had time to solve 14C after having a break where I went shopping, and then I have to make dinner. And then tonight I'm playing bridge. So that's the plan. Now in 14b we showed this equality, and now we have to find f as a function of lambda, so it equals this. And when we consider that was the wrong exercise. When we consider 14a, we have it. We can't help thinking about this integral, can we? So we'll make a power expansion of this 1 divided by square root 1 minus lambda t and now how is that? It's minus a half over n minus to the nth lambda to the nth t to the nth. Isn't that so? I'd usually look up these things, so sitting like this and doing it. And it's minus 1/2 1, that's n equals 0, minus a half nt plus 3/4 lambda t squared minus 5. Yeah, then comes it slightly difficult. So 1/2 minus 1/2 minus 3/4, 3/2, that's 3/4, divided by 2, that's 3/8. No, that was 3/4. Now we get also minus 5/2, so that's 15 8 times 3 factorial of 3 factorial, that's 6. Etc. Now, nth part. So it's minus to the nth 1, 3, 5, and here n was 1, n 2, n 3, so it's 2n minus 1, so if n is 1, it's 1, 1/2. If n is 2, it's 3. Halves, and then divided by n factorial, lambda t to the nth. So that is the nth term is minus 1 to the nth, 2n minus 1, double factorial, 2 to the nth, divided by n factorial. Now let's see, that agrees with that, so, and then lambda t to the nth. Now what's the radius of convergence for this guy? So just take the proportion between two consecutive terms. There is a factor 2n minus 1 halves, a factor n, and a factor lambda. And as n tends to infinity, this tends to lambda. That means the radius of convergence is 1 divided by lambda, which is larger than unity. So it converges from naught to lambda, so it converges uniformly from naught to unity. So we have uniform convergence of the power series, so we can integrate each term in its own right. All right, now we have to use the result from 14a, which I naturally have forgotten. Pi divided by n squared. That's weird, that's the same. It's as if I've done the same thing twice. Strange. Oh, it comes in, it does come out squared. All right. So this was pi divided by factorial of n factorial. And then let's write this 135 divided by, we do it the same way. Lambda to the nth. I seem to have forgotten this guy. So it just needs to be put in here as well. So it's pi times 2n minus 1 double factorial, 2 to the nth, n factorial, all this squared, minus 1 to the nth, lambda to the nth. Now, what was the expected result? Pi, divided by the red one, I forgot in once more. And then all this squared and squared and there, that's what I get. That's my hypergeometric series, and it's now 5 o'clock. I have time enough. So let's do the last one. We have to derive the differential equation of the hypergeometric series. Oh, where was the sum and the red guy? So we'll just take only the essential part. And just forget only the sign and the independence here. So it's minus. Was there a minus in the answer here? No, it's no minus. That's very weird that there's no minus. Oh, there are two minuses. There's one coming from the there's one coming from the minus lambda to the teeth. So there's one minus coming from here, being exponentiated, and then one minus coming from this guy. So we should have a minus in here all way, so it should be plus all way through. So I'll just do it here. So it's minus lambda t, minus lambda t, minus lambda t, so it becomes plus all the way through. There we go. And then lambda to the nth. So we differentiate it twice. It doesn't work. Let me use this guy. And then we re-enumerate. So, times lambda to the nth, and then we differentiate once more. And that gives another n, so it's n minus 1 here. N plus n plus 1. I was a little ahead of myself. Oops. Yeah, that's correct. And we substitute n for n plus 1. So, let's have a little help from the solution. So we want to come up with this, and since this have a factor 4, they use 1/4 in front of f of lambda. So it's just use that, and then a times this. Oh, we take the double derivative first, plus 3. And then we forget the power of n. So it's something with 1/4 of f lambda, and then we find a and b, the coefficients to the other ones. A times this one squared divided by n factorial, n plus 2 factorial, plus b times this, and here's a factor 2, so it must be a Now, what did I do here? And then b must have a factor 1/2, I think. So let's, to forget those factor 2's, take b divided by 2 here. So this all cancel from the beginning. B times and then n minus 1 factorial squared divided by n factorial squared. So we have to find a and b so that this is fulfilled. So there's a lot of cancelling going on. So first of all, we divide by 2n minus 1 double factorial squared. And then we multiply by n factorial squared. So here we have n plus 2 times n plus 1. And here we have the same. So let's multiply by this on both sides. So we have actually 3 equations with 2 unknowns. So the fourth order, 4n to the 4n squared, that's 16 n to the fourth, which vanish with nothing. Actually should have more n's in the denominator. Here n has been added twice, so it should be twice bigger than that. So it should be 2 n's more than we have here in factorial. And here should only be, and in B should only be 1, and that's not what I see. Oh, I see it here. Here it is, all right, so we get n plus 1. Yeah, this part with B makes sense. So it's down in the second one. I don't like it. This is the same. And then an n, lambda minus 1, n times n plus 2 factorial. So we get 2 down there, n plus 2 times n plus 1. And what do we get up here? We only get n plus 1. So here I've been copying from the wrong guy. So backstepping a bit. So that's the usual thing, that it stops working suddenly. Now, A, so we multiply by n squared, so it gives A plus 2 times n plus 1. And here we only get n plus 1. So this is second order, this is first order, not what I like. B times F mark. So were we doing down here? 16 n to the fourth. Why on earth do I do that in one foul stroke? This is actually annoying to do by hand, so let's Mabel solve that, and then we can see if it gives the right result. Oh, this is terrible. Now, we need to have Mabel rather small, and then this one goes behind it. I need the light on the keyboard, so excuse me. That was better. I'll just make it somewhat larger so that you can all see clearly. And we only have one term n to the fourth. I thought we should have two. This one times... Oh. So, I'm still doing it wrong. You know what? I'll just look at it tomorrow, where I should have plenty of time. And then doing it on a blackboard like this is not optimal for making algebra correctly. It was much more easy when I had to find out that convergence was uniform. You know, that's nice, that's easy. But all this algebra, that's really complicated when I'm recording. So leave it for today. So I'm back again. Now, yesterday I failed wrapping up the section 6. I failed in 14D. So that's what I intend to finish today. But first, I looked up some of the functions that were used. Now, first of all, when I computed the integral in Mabel, then it gave the elliptic integral, the complete elliptic integral, not the hypergeometric functions. So that was interesting. I needed to know why. So I looked up, what did I look up? The elliptic integrals. And then I found this being exactly what we needed. This is the integral we've been performing time and again. And now by writing it this way and setting t equal to sine theta, we get exactly the elliptic integral. It's a simple substitution. So we should have noticed this. We should, but I don't think I did. No, I didn't. So that was very nice. Another thing, the elliptic integral has the expansion. Oh, I need to remove this picture. Oops. Now I've done it again. So I'll just check that I'm still recording. That wasn't it. That's the guy. Yeah, I'm still recording. So we can put it on a little later, and I hope it works. Now, the elliptic series, I'm taking the first terms here. So that's it. Now we should go to the hypergeometric functions, and they are defined here. And all these photos are from Handbook of Mathematical Functions, Abramovich-Steggern, the one I bought while I was studying. So here we have it with two parameters in front of the first semicolon and one parameter after. And it satisfies this differential equation. And if this has to agree with the differential equation in 14D, I haven't a picture of that. I hope you can see it. Then C must be equal to unity. This must be equal to 2 and AB to 1/4. And that means that, well, C must be unity and A and B both be equal to 1/2. So that's the hypergeometric function. 1/2, 1/2, and C equals unity. What are the series of that? And it agrees totally with the elliptic integral, except that now here we only have the even powers of x, and so that's this. So z equals x squared. Then it's the same one. So it's the same series really. So that means the elliptic integral comes as a special case of the hypergeometric series. Now, it was defined by Pochhammer's symbols. Yeah. And they are defined such that A3, for instance, equals, let's do AN, the general definition. A times A plus 1 times A plus 2 times A plus 1 minus 1, so that we have n factors altogether. In particular, 1n is the factorial of n. All right. So that was the connection between the hypergeometric series and the series in the problem and the elliptic integral which we encountered. So let's see if we can get this guy. No, doesn't work. Sorry about that. Now, This is the hypergeometric series of problem 14D, and I'll use it with Pockhammer's symbol and then see if I can do that. So we differentiate and change variable. Oops. Oh yeah. And then differentiate once again. And I should be able to say that, no. Oh yeah, another n is taken there, and that's all that happens, so it becomes all right. And so we want to have a f double mark plus b derivative of f minus a quarter f vanishes, and this is an identity for all lambda, so that must hold for the equal coefficients. This for each n. Oops. Let's see if I can go back there. Oh, I couldn't go all the way back. So, A times this guy plus b times this guy minus quarter there we go. We should find a and b, so this vanishes identically. So we divide by this symbol and multiply by n factorial and n plus 2 factorial. So this gives 1/2 plus n plus 1 times 1/2 plus n. And we multiply by these two. And and it's like squared, and this gives 1/2 plus n squared, and then we get n plus 2. This cancels, and then we multiply by n factorial, so that one of them cancel, and then we have n times n plus 1 left. So this is square term, this n to the 4th, and this gives n to the 3rd. So I do get the same impossibility as last time. Now this is very interesting. I thought I just made a silly mistake that I would be able to do right today. So what I'm doing now is trying to reconcile just those two terms. seems that every time we differentiate, because of this being squared, we get another power of n. And that's what's happening here. N to the second, n to the third, n to the fourth. So, I'm doing something fundamentally wrong. So we just take a break here, and then I'll take a look at it. And then I'll just present the solution when I've found it. So I'm on it after a very little break, realizing that we cannot find constants, of course, and in the exercise they really don't want constants. Now where do we... recent 114a. So they're not looking for constants, they're actually looking for lambda is the variable. So exactly the problem I have encountered is solved by adding with a second order, multiplying by a second order polynomial and a first order polynomial, so that we do get the same terms in the end. So here this should be multiplied by let's erase what we don't need. So now that has stopped. So now it's trivial. Now there's no problem in doing it. So it's just a question of verifying it. And I've fucked it so much up. I won't do it. So back again. I did it straight away. And when I was offline, I was able to do the arithmetic. So I'll just show it to you. There we go. So I differentiate twice, then I multiply the derivative with 1 minus lambda, call it a, and the second derivative with this guy, calling that b, and then we add a and b. So first these two terms, all this agrees, so it's n plus n squared minus n, so we just get n squared here. And the same thing happens here. 2n must be added to that, giving n times n plus 1. And then we substitute n with n plus 1 here, giving this guy. And we put all we can outside the parentheses, and then this is all that's left. And I was able to simplify that to 1/4. And that was what we had to derive. So in the end, I was able to do it. So it won't come online. All right. So that was the end of section 6. And it was really, really educational, I must say. So thank you very much.